Well, I was born in Detroit, Michigan, and did various things in Detroit before I went to work for General Motors. Actually went to work for for Cadillac Division during the Korean War and worked on the T-41 and light tank. I worked in Cleveland. We worked out the tank plant in Cleveland, Ohio. And then I was drafted into the military and spent 2 years during the Korean War with the Ordnance Corps at Aberdeen Proving Grounds, working on track-laying vehicles. And then when the war was over, the Korean War was over, the whole crew that was in Cleveland, including Ed Cole, who was the plant manager down there, had gone to Chevrolet. And their chore at that point was to develop a new Chevrolet, which is the 55 Chevrolet. And so in the spring of '52, I joined Chevrolet back in Detroit again after I'd gotten out of service. The original engineering was on what they called the annex of the General Motors building on Milwaukee, which was on the back side of the GM building on the boulevard. And then our test lab was out at the gear and axle plant, the Holbrook gear and axle plant. We had a test lab out there, and the engineering garage was also at Holbrook. Mm-hmm. And then can't give you the exact dates, but then later the Chevrolet Engineering Center was built at the Tech Center, so that everything was moved into the Engineering Center, the new building. Design, test, preliminary prototype build, everything and experimental shops were all in the Engineering Center. In those days, the competitive activities of the GM division, all 5 car divisions, all had their own, and they were as much competition as our competition cars were within the corporation. So you pretty much did your own thing. And then it was in later years we then started to do some consolidation back in the late 70s when the so-called first X car was developed that was then an offshoot of the car divisions through a coordinated program. Well, I first got involved with SAE when I worked for Chevrolet. And in those days it was called the Defroster Committee. And the Defroster Committee wrote the MVSS 103 defrosting requirements that is in the federal standard for minimum performances of defrosting systems on front windshield. So I was in the committee on that. I was not the chair in the early stages. At some point, which goes back in history, we can't even seem to find anymore, it's so long ago, I became the chair of the committee. And it was that point that we expanded the committee and called it the Interior Climate Control Standards Committee. And then we, into that time frame was the major transition from CFC 12 to the new refrigerant, or the global warming issues that were involved from the Montreal Protocol. And then the committee was then expanded. We were commenting earlier today with the group out there, we used to have 80 to 100 people in those meetings, and we worked on all of the engineering requirements and the transition from CFC 12 to 134A refrigerant, and plus additional stuff on carbon dioxide, 152 refrigerants, and also obviously 1234YF. I retired from GM officially in the spring of 1981 after I retired under the 30-year and out provision. And I had been, my crews, we spent pretty much probably through all the latter part of the 70s down at the General Motors Desert Proving Ground, which was then in Phoenix. It's no longer there. The test facility is now at Yuma. But we basically would go in there about the middle of June and stay there until the first part of September. And we would work on air conditioning systems and engine cooling system developments. We also did some hot fuel handling projects. But we basically would take up residency in the summertime. And then as the time went on, when we decided to go into automatic temperature control systems, we started running fall and spring trips because the neat thing about the Phoenix location is that you're at roughly 1,100 foot elevation in Phoenix, but Flagstaff, which was a little over 2-hour drive away, was at 7,000. And so you'd look for a 25 to 30 degrees difference in the daytime, and as much as a 40 to 50, 60 degree change from the high in Phoenix in the daytime to the low at Flagstaff. So you could go ahead and make a 2-hour run on the automatic temperature control system and get at least a 25 degree, maybe 30 degree ambient swing, and make the run between Flag and Phoenix, Phoenix back. So we used to drive to Flagstaff and stay overnight, get up early in the morning before the sun's up, and run a warm up in the morning if it was cold, which it generally was at that time in spring and fall, and then back to the valley. And of course it had been a warm day in the valley the prior day, so we'd run a soak and cool down and take off for Flag and warm up in the morning, and then another trip back to Phoenix. That'd be our run for automatic temperature control. I can't tell you exact date, but we had it available on the full size of the B-car chassis. It had automatic temperature control available as an option, as well as manual. As time went on, the corporation developed a standards committee, which then actually was chaired by Pontiac. And then we would meet and we'd talk about standardized systems. And as time went on, we did have standardized systems on the full-size Chevrolet, the B-car, and on the Pontiac, the Buick Oldsmobile, and the C-car Cadillac. So we did have engineering coordination programs, and there were coordination programs on automatic temperature control, condensers, compressors, all of the components that were in the systems did emanate from a so-called engineering standards committee within the corporation. That was done in later years. But again, each one of the divisions had their own autonomy of what they wound up doing, what they did for outlets on the instrument panel and so forth, but the refrigerant cycle side would be somewhat coordinated. I would say at that time that probably at Chevrolet we had the largest development group in the corporation. The other divisions may have had a design engineer, a test engineer, maybe 1 or 2 technicians, but we had a design group that was responsible for basically pushing the lines on paper, which in those days we still had drafting boards, didn't have computer designs at those points. And so we had about 8 or 9 people in the design area, and in our test and development area we had as many as 21 people, engineers and technicians in that area that we basically had to make the products work. And as I say, at that point we had engine cooling along with the heating and air conditioning and ventilation systems. We even used to build ventilation systems. If a lot of you will not remember, but we did have ventilation on the car before we ever had air conditioning to the degree we have it today. And those are the days when we did the so-called astro vents, where we plumbed the air conditioning outlets, if you were, directly to the plenum, so that you could get ambient air both at the floor through the lower vents and also coming out of the panel out outlets on the panel. You had shut-offs on them, you could control them and so forth. So when the gal sitting next to you wasn't happy, she could shut her outlets off and you could have all the air coming in on you. It was, you had a cowl plenum that was part of the body structure. And the cowl plenum then had an air intake at the base of the front windshield. And then that went out into a horseshoe affair, and then the summer vents were down here on the floor. And then the upper level vents then went directly into the plenum area at the top. So you had air coming into the base of the windshield, into the plenum, available out of the upper vents or down into the saddlebags onto the floor. So you in effect had 2 floor outlets and 2 panel outlets. Right, that was just ram air.
Right.
And that's the kind of stuff we used to come down to Florida here and run tests on, and we found out where the transition was of what the sunny day, whether it was a sunny day or a cloudy day, on when you'd run out of ventilation, when you could have to open windows on cars, and so forth. And then we found out that roughly a sunny day, about 60, 65 degree day, you were in an air conditioning mode. You could not ventilate the car with outside air or leave the windows up on a sunny day about 60, 65 degrees. You had to have some form of cooling. You had to reduce the air temperature coming into the car. You could not take ambient temperatures in. If you go back through the history, the situation, it's rather interesting. I will be presenting at SAE tomorrow. If you remember, the Cadillac, Oldsmobile, Buick air conditioning systems were in the trunk. And they also had the little ears on the back, little chromed ears, body color and chrome ears that were on the back, on the top of the fenders. Well, they basically took in 30 CFM of outside air through those little vents. And the philosophy was to get rid of staleness in the car, try and pressurize the car a little bit with some outside air into the car. And they had a 220 CFM system, two-blower system, that pumped the air up out of the rear package shelves. And as the exotic ones got better, actually into the headliners with the outlets and the headliners. But some of the original ones just had a plastic duct, and it blew all the air from the rear package shelf forward. So those were some of the first systems that were in production at GM, and there were some other similar ones in production at Ford and so forth. But back in the 50s, the real air conditioning experts, if you will, at this point were the Texans. Because they basically saw a need to provide some way of cooling the car in their hot, humid climates that they had. So that created the air conditioning industry as such, with a cooler box that bolted underneath the instrument panel. It was strictly a cold air device, had some form of minimum temperature control, but did provide you a pot-bellied stove, if you will, in reverse, a cool spot in the center of the car that you could drive along. It was back in those days, if you go back and look some of the research, Vornado actually made a device that was kind of like a torpedo tube that mounted on the right side of the car, and it was an evaporative cooler, and it was filled with a material that you could fill with water, and then as you would drive, the air would come in the tube and then blow in through the partially open window that you had this thing put into. And so that was some of the early days of attempting to condition cars. So if you think about something back in the 40s and the 50s, in that time frame, the real innovation took place in the Texas market, the Dallas-Fort Worth market, where they built these hang-on units or box units to cool. And then they progressed a little bit and started doing a little bit of the involving it and putting it behind the instrument panel and so forth. But it wasn't really until probably the 50s and then on into the 50s and the 60s that true temperature conditioning, four seasons air conditioning, if you will, really came into fruition, because that's when we started combining the heating air conditioning systems, providing different methods of getting the air out of the systems and into the car. Ford did the mixed air heater. I can't tell you the name of what they called it at the time, but I don't know who the engineers were or who the people were behind it, but they developed the first mixed air heater. And I believe they called it a blend air, if I remember correctly at that point. The fallacy that they had, that the first thing was in production, is they did not do a very good job of temperature mix. And the customer complaint was that you could have cold air coming out of one side of the heater and hot air out of the other side. But the real problem goes back that in those days we had a water valve, which at GM it was called a Ranco valve, and the water valve basically was on the capillary tube was placed on the face of the heater core. Now this water valve would then modulate the amount of water that was flowing to the heater core. The problem was that when you go to idle, the pump was not developing 3 gallons a minute to saturate the core, so the discharge air temperature got cold. So then as you would take off, then it would go hot and then it would go cold, and finally it would regulate itself out. But that swing could be much as 10, 15 degrees. And if you were down to the point that you were just slightly above body temperature, that would be blowing cold air at you. So the mixed air heater eliminated all that, because the mixed air heater, or blend air, whatever you want to call it at the moment, is that once the core is saturated, you can dump all the water you want through it, and it's not going to give you any more heat. But the end result was the core remained saturated, and when you would drive the car, you could practically print a straight line on the discharge air temperature. So then the next thing was get it to mix and make sure that you didn't have a spread that was going to be felt by the occupant in the car. And we used a rule of thumb about 10 degrees. If you had anything over a 10-degree spread across the outlet, you had a problem. Same thing with the AC outlets. So what I did is I looked at the Ford system and I said, hey, this water valve system that we've got right now would be very easily to adapt to. And so we would just reduce the length of the heater core, and we put a little 8.5 square inch hole in the right-hand side of the heater assembly, so that the air inlet on the outside, when we put that door in there for temperature control, just came around a short corner and went right by the face of the core. So that is where we first went into production on that. Chevrolet put that into production, and then later the rest of the corporation started to pick up the mixed air heater. So then to answer your question as you did a minute ago, or a question a couple of minutes ago, is that I was sitting in the office one day and I said, you know, we've got all these controls, we've got all kinds of problems. We don't have good temperature control on the air conditioning system. We had cycling clutch system, we had hot gas valve systems, we had suction throttling valve systems. I go on and on and on. And you basically did not have very good control or over an ambient range swing of getting a decent control of the discharge air temperature. It was always too cold. It never really did the job. And the other thing it did is that you got into re-evaporation odors, because if you elevated the evaporator coil temperatures above freezing, then you were not doing maximum dehumidification. And if you weren't doing maximum dehumidification, you then might be re-evaporating the or recondensing, I should say, and then re-evaporating the humidity in the case, and then you got evaporator odors, the laundry smell, or undesirable odors. So I was sitting there and I said, well, you know, why don't we go ahead and put the heater core in this position, then put a mixed air door, bring all the air through the coil, bring it down to 32 degrees, and we don't have to worry about the evaporator getting above freezing. We're always going to dehumidify, and then we either let the fully dehumidified air head right to the outlets, or the blend door, mixed door will come in and we'll bleed some through the heater circuit, and we'll warm it up, and we can put out 75-degree air or 60-degree air, whatever we want, but we're always going to be max dehumidification. Well, the issues then, as we got into the environmental aspects, was, well, you're wasting all this energy. So the current offset, which is part of the AC-17 requirements, or to meet fuel numbers, produces an offset. And so instead of running the coil at 32 degrees, when you get above a certain ambient, or depending on what your control function is, you set it up. Well, some of the problems, we're getting complaints from people in the field that they're getting re-evaporation odors. Well, what may very well be happening is that going from 32 to 42, if there's a hot spot in the core or something of that degree, you may wind up exceeding the re-evaporation characteristic, and so then you get re-evaporation odors off it when you're in the offset position. But you've got this offset in the cars today for fuel economy numbers. How much it really benefits, I don't know, but we do have problems, and we do have odor problems with the offset coils. There was a big activity to put coatings on the core, because as they tried to make the cores more efficient, they did not drain. And so then you had see, if you go back to the old Chevrolet 55 system, the Chevrolet 55 system was a similar offshoot of what was made in Texas for the hang-on units, and the hang-on units were basically tube and fin cores. They were copper tubes with a complete stamped out piece shoved onto the copper tubes. In the case of the Chevrolet system, Frigidaire developed a button tube where they had a button like this, and that button stamped out aluminum fin went on the face of went on the copper tube, and they were all stacked onto the copper tube. So we had this button tube core. Well, those would be fairly free of accumulation points because they were relatively smooth fins and so forth. Then with the advent of the plate fin cores, which were then used by most of the car manufacturers, those air centers, to be more efficient, became more and more complex. And so they did not drain. And by not draining, then you could conceivably, when you shut the system off, or if you were a cycling clutch system, and you had the on and off cycle, which a lot of the systems were cycling clutch systems in those days, cycling the compressor for freeze protection, then if you didn't drain the core, you'd start to get odor problems. So then the questions came up at this point of what do we do? Well, we'll coat the core. And today, some people still coat cores, some do not, and we're getting back into some of the odor problems.
So coating the core solved that?
Yeah, but the only problem was we didn't know how long the coating was going to last. And the other thing is that if you live in Florida and you live in New Orleans, you're going to be more susceptible to moisture accumulation and contamination and odors. In Arizona, we don't have the humidity, so our wet bulb isn't there, so we don't really have much water. Matter of fact, if you're driving along on the road in Michigan or Florida and you're running the air conditioning system, you see the condensate dropping out on the road. Very seldom do you see condensate drop on the road in Arizona because our wet bulb is so low. When it gets up to 25, 27%, that's peanuts compared to 60 or 70 or 80% if you're in the Gulf states. Well, let's talk about the POA valve. When we did what we called the series reheat system, which I called the Q system originally, when we started the development of that, we, in that particular stage of the game, had the old STV valve. We had two versions of the suction throttling valve, the STV valve. We had the one with the mechanical lever on it. When you moved the temperature lever, you would change that and would change the setting, the evaporator pressure setting, by changing the lever. The second one that we had in that time frame that we were working on, we had a little vacuum diaphragm. Well, let me back up. That was stopped at this point. When we had the mechanical suction throttling valve, we wanted to take the lever off of it, and we wanted to always to control at 29.75 psi gauge on the evaporator absolute. Well, we brought the first Q car that we put together to Phoenix, and we decided that we were going to go to Flagstaff, see what happens with the weather change, Flagstaff, stay overnight. By the time we got to Flagstaff, there wasn't any more air coming out of the outlets. And we couldn't understand quite what happened to our airflow. But when we got to Flagstaff, we cut some holes in some of the ductwork, and we had a block of ice on the core. Well, the problem was that this mechanical STV valve was basically reading gauge pressure, if you will, of such. And when you would go up and you lose the difference between 1,100 foot elevation and 7,000, the core froze up. So obviously the mechanical suction throttling valve without a cable on it wasn't going to resolve our problem. So the first issue that we did at that point is we took the mechanical STV valve and they put a diaphragm on the top of it. Frigidaire did this work. Put a diaphragm on the top of it and it offset us 2 or 3 pounds. And then we put on the control lever, when you move the temperature lever off of full cold, it would take it from 30 pounds to 33 pounds or something like this, and then we hoped we didn't freeze the core up. But in the meantime, when we got to Flagstaff that night, we called back to Dick Widdowson, who was the control guy at Frigidaire, and say, Dick, we got a problem. And Dick says, yep, I know what your problem is, I'll work on it. Well, anyway, he developed the POA valve, which was the one that had a little aneroid bellows in the inside of it, so it always controlled on an absolute pressure, and we could drive from Phoenix to Flagstaff to Denver, and we always had absolute pressure on the core, and it never would freeze up. And so that's where the POA valve came from in the progression from mechanical STV to vacuum operated to POA, which is pressure operated absolute is what POA meant. Well, the orifice tube we put into production, I can't tell you the exact year. The first vehicles we put the orifice tube on were the Vega and the C truck, and then it eventually went on the passenger cars and Chevrolet, and then eventually on the corporate systems. The advent of the POA, I'm sorry, the orifice tube was, we had a lot of problems with expansion valves in those days. We'd have noise, we'd have evaporator freeze-up problems, which was caused by the desiccant we were using in those days. But the expansion valve was expensive to make and had its problems. So one of the engineers that worked for me originally had been in the commercial sector, and we got talking about the fact that you use capillary tubes to feed the distribution in a household evaporator assembly instead of an expansion valve as such. So then that basically, we got Dick working on developing the orifice tube, and the orifice tube basically was used by quite a few of the different manufacturers over a period of time. They were different sizes, 067, 072 diameter ones, and we had later, when the situation came up that they wanted to drop the orifice tube, we had been working on a two-stage orifice that would then improve some performance at city traffic versus having a single stage that would always run the full saturated core regardless of what speed you were running. There was a lot of politics involved and so forth at that stage of the game, and there was the question also of fuel economy. And the expansion valve, the TXV, block TXV and so forth, you could then tune it to give you the control flows that you wanted. And that's where we were headed for with the two-stage orifice, to try and then reduce the flow so that you weren't pumping the total amount of refrigerant running a saturated core. Because with an expansion valve, you know, you've got to set the superheat up on it, and if you've got a core that's got high airflow in one corner of the core, it's pretty hard sometimes to get rid of hot spots in the core. Whereas with the orifice tube, you're flooding the core, and the core is going to be pretty much the same temperature over the entire face of the core, but you're flowing a lot more refrigerant. So coming along with the expansion valve, or block expansion valve, began to start to show its interest at that point. The expansion valve would then allow you to meter under low loads, different driving conditions and so forth, flowing less refrigerant. Now, how much in the real world did it save in fuel economy? I don't want to even get into that area, but we did show without question that the expansion valve would give us better performance from the standpoint of energy requirements as to the orifice tube. And so that's basically what moved the orifice tube out of production.
Right.
I first got involved with MAX with the first CFC conference that the EPA held in Washington. There were probably 25, 30 people that showed up. And of course I was chairman of the SAE committee at that particular point. And that's back when SAE meant Society of Automotive Engineers. People still think it means that. Today it's SAE International because it has boats, airplanes, cars, trucks, and everything else. So the interest is mobile air conditioning was a big concern in the energy issues. And at that meeting, I met Simon Oulouhojian, who was president of MAX at that time. And Simon and I got along pretty well. He was 2 days younger than I was. He was born on the 6th of September, and I was born on the 4th of the same year. And so he was considered my little brother, my younger brother. And Simon and I developed a pretty good rapport. And we looked at the situation as it was at that point, that Max was basically an outgrowth of the Texas operation, and it was the next level up. But what it also deemed to be a point of concern is that it did not have access to the engineering capabilities to look at these cars as the car manufacturers were doing in those days. So it was Simon and I to agree that what we would do is attempt to develop a relationship between SAE Standards Committee, Interior Climate Control Standards Committee, and MAX. And so we developed that rapport and started holding joint meetings like is still done here, will be tomorrow, for example. And so we built that growth up, and then Simon and I were very active in a lot of the CFC activities through both the EPA and also through the United Nations activities. Well, we were involved in it. Simon and I, both and I, were one of the original honorees of the Montreal Protocol, and also were covered out of the best some 10 years later. Also Jim Baker was involved in that area. So, but Jim Baker from Harrison in those days, later known as Delphi, Jim Simon and myself were probably the mainstays of the mobile air conditioning activity on the entire international basis, because we were involved, and I used to chair an ISO committee, and I also chaired one of the United Nations committees that we basically were looking at where we were going to with new refrigerants and new system designs. The issue at hand is that when the Montreal Protocol was created and brought to fruition, is that the major concern was ozone depletion. Global warming was a discussion that was at a much lower level, but the GWP, as we call it today, global warming potential of refrigerant, was not even a point of discussion at that point. The real big issue was the depletion of the ozone layer and the fact that CFCs were the major cause. The CFC issue being the major issue is that there wasn't even a discussion what the global warming number was of 134A. It had 0 ODP, and ozone depletion was what we were after. Now, a little bit of the history of 134A, it had been around for a while, and if I remember the story correctly, DuPont had actually been running some refrigerators in a very long-term program, household refrigerators, with 134A. And so in one of our meetings in Washington with the EPA, the discussion came up about 134A. Well, some of the engineers said, oh, it's going to be years before we can develop a plant that will go ahead and produce 134A. But it became a candidate because they knew something about it. It had been around for a while, and it had 0 ODP. So that became the candidate to go ahead and replace the CFC-12.